the range of engineering properties for soils vary widely depending on the soil type. So today we're going to be looking at the process of soil identification in two different ways. One of the ways is a rigorous classification of the soil according to a very specifically controlled soil classification system. In this case, we'll be using the Unified Soil Classification System. This is a lab-based approach, and there's an ASTM standard that specifies very clearly what properties to measure or characteristics to measure in which to place the soil in a specific box or category that collects that soil with other soils that are somewhat like that. So the characteristics we're going to be looking at in that case are the gradation, that is the range of particle sizes and their distribution, and the plasticity characteristics of the finer portion of that soil. So the answer to the question of what box it falls into is going to take the form of a 2 or 4 letter designation, such as a high plasticity clay, or clayey sand, or well-graded gravel with low plasticity silt fines, or something like that. So the classification then is a box in which we're putting the soil, but it's not telling us very much beyond that broad grouping. So we're also going to be interested in a soil description, and this is something that's often applied in the field. The classification is based on measuring precisely some characteristics, but often we want to make a soil description while we're out in the field, we're logging a boring. We want to be able to describe in the boring log what soils we're encountering at which depth. And so as a field engineer, we're called on to estimate the soil's classification. That's one part of the description. But then we also want to add a lot of verbal descriptors of what is distinguishing about that soil. How is this silty sand perhaps different than the silty sand we encountered at a different depth, maybe even in the same boring or another boring at the same site? And so there's another ASTM designation for visual manual classification, in fact, and these are based on observations that we make rather than on precise laboratory tests. And what we're going to be looking at is characteristics of the soil overall, particle size, range, and distribution, certainly the angularity of individual grains that we might see, approximate plasticity of the fines, not a numerical value, but a sort of range. We might be interested in the color. That would help us distinguish the material. What level of moisture it's at. Is there a distinctive odor or not? If the soil is dried out, some soils will exhibit a much higher dry strength than others, even if they seem similar in their moist state. And then the dilatancy is a measure of how easily water can move in and out of the sample. So that's often a distinguishing characteristic between silts and clays, as we'll see in the lab that we're going to go through. All of these characteristics are true for the soil in any condition, as is the classification, in fact. But then there's also some things, if we're encountering the soil in its natural condition, if it's an intact sample, we can also say things about the consistency of the soil or its stiffness. Very stiff or soft, somewhere in between. The structure, is it laminated? Does it have slickened sides? And is there any cementation holding the grains together that might be lost if the soil is disturbed, if you get a bulk soil in the lab? So today what we're going to do is look at 6 soil samples, and we're going to walk you through the description portion of this, which will include an estimate of the USCS designation, and just talk about how we would make that description. So here we're seeing soils 1 through 5 around the outside of this plate in little cups. They're dry bulk samples. The 6th sample is the one intact material. It's taken with an undisturbed sampler. In the center in a cup is soil 3A, which is related to soil 3, and soil 4A is the loose little spear on the plate there, related to soil 4. And that's shown also on the data sheet. We have sort of a map showing these soils, and your task is going to be to fill out the descriptions and classifications of the soils as we talk through them. So we'll start by looking at soil number 1, located near the top of the plate. And our first decision in trying to classify a soil or estimate the classification for a soil is to decide whether it's a coarse-grained soil or fine-grained soil. And that's controlled by this sieve, which has 200 openings per inch, or it's called the number 200 sieve. The openings are very fine, about 75 microns in size. Particles that fall through are fine-grained particles, and particles that are retained on the top of the sieve because they won't fit through are considered coarse-grained particles. And so in terms of the soil overall, we need to estimate, according to the system, whether more or less than half of the mass of this soil will pass through the number 200 sieve. And as you may be able to see, this soil consists of considerably larger grains. We also could observe pretty quickly that they're all roughly the same size. That's a very useful observation too. And in fact, virtually no particles in this soil will pass through this sieve. So that tells us right away that we're talking about coarse-grained soil. And so we need to decide if it's a sand or a gravel, and for that we need to look at the number 4 sieve. It has particle openings between the wires of about 4.7 millimeters, so much coarser, much larger. This is the boundary between gravel particles that would be retained and sand particles that would pass through. So looking at the soil again relative to this much coarser sieve, would we estimate that more or less than half of the soil would pass through? Hopefully it's pretty clear looking at the particles here that virtually all of these particles do pass through this sieve, and that therefore this soil is in the range, most if not all the particles are within the range between these two sieves and are therefore makes the soil a sand. Since the soil has virtually no fines content either, that leaves us with a simple determination to make of whether the soil is well graded or poorly graded. Our only two choices left in the Unified Soil Classification System are well graded SW or poorly graded SP. And to be well graded, we need to have a wide range of particle sizes. We need to have the D60 from your gradation curve divided by the D10 to be greater than 4. And that might be a little hard to imagine without running a sieve analysis and plotting things up, but just for your experience, to give you sort of a calibrated eye, these particles are similar enough in size that that ratio is only about 1.7. So much less than 4. So this is not broadly graded enough to be a well-graded sand. So we're left with a poorly graded sand, SP. I'm going to talk you through the first few here as we go. That's just the classification. What else might we say about this material to help distinguish it from other poorly graded sands? The fact that there are virtually no fines is actually important, and we use a special term for that. We call it a clean sand. The fact that the particles are quite similar in size would suggest we would probably use the term uniformly graded, meaning all the particles are about the same size. So those are all terms that I would include in the description of the soil. What else can you note? Remember, we talked about things like the particle color. I'll let you decide what range of colors you see here. Another thing that may be harder to see in the video is how rounded or pointy and angular are the individual particles. And you can only do this with soils that are sufficiently coarse to really see the individual particles. There's a significant range in this material. Some are subangular, meaning that they're not extremely pointy but relatively elongated, while others are more rounded. And that's typical for many soils. There's going to be a range. So often we would apply a range in the description and say that this is subangular to sub-rounded. We can't say anything about the state of the soil in the field. We don't know if it was a loose sand or a dense sand, because now it's just dry sand in the laboratory. So we have to restrict ourselves to characteristics that we can judge here back in the laboratory. All right, so I'll let you write down your description for soil number 1. Moving on to soil number 2 now, let's see if we can describe that, estimate the classification. Much less range in color than soil number 1. If I pour a little in my hand and spread it out, you can see the individual soil particles are much smaller. So we're going to go back to the Unified Soil Classification System and answer that first question with the number 200 sieve. Do we think more or less than 50% of the mass will pass through this sieve or not? And this is going to be a very difficult thing just looking at the video to estimate, because the particles are much closer in size than soil number 1 was to this mesh. But I'll just have to let you know that in fact the vast majority of these particles will still not pass through the number 200 sieve. And in fact, perhaps only a few percent, 2 or 3% of the particles would pass through. So, although it looks very different to soil number 1, it's still retained on the number 200 sieve. And of course, it will all pass through the coarse sieve. So it's again going to be a sand, much like this was a sand. So we're back to that question. We have only a few percent fines. What are our choices again? It can be well graded or it can be poorly graded. And the key question there again is, what is the range of particle sizes that we see? And the fact that nearly all the grains are hard to see individually suggests that there can't be much range, right? There aren't large sand particles in here. This is all a fine sand. Okay. So if it's fine and uniformly graded, it's again not going to be well graded. So we're seeing that this soil is also an SP. So soil 1 and soil 2 are in the same category, even though visually they're very different soils. And that's one of the reasons that we want to include these soil descriptions to help differentiate between them. So as part of your soil description, you want to mention things about the size of the particles, that they're fine. You probably should mention again that it's uniformly graded. How in the field do you think you might determine whether there are any fines or not? That's a difficult question to answer when the soil is dry like this, especially because particles that pass through the number 200 sieve are sort of at that boundary where you can't see an individual particle. So how can you know how much of it is present? And the answer is to get the soil wet. So we have a little test tube here in the lab. Out in the field you could use a mason jar or something like that. We're putting the dry soil in. We're going to add some water. And how is this possibly going to help us decide what sort of fines content there is? What do you think? Well, if we mix this soil up in the water, so we have a nice uniform distribution of the particles, and then we let it settle out and watch it with a little time, we see there's some clouds in the water. You see how it takes a little time for that cloud or that settling front to settle out. So those finest particles that are the longest in suspension, those are the particles that would pass through the number 200 sieve. But there's very few of them. The settling front clears out very quickly, and the remaining soil in suspension is very, very small. So this is what tells us that this is a sand, not a fine-grained soil, and that in fact there are not many fines present. Let's move on to soil number 3, which is here near the bottom of the plate. And this looks like gray powder. The mass of the soil in the cup is, of course, is not as full, but it's comparable, perhaps in density, to soil number 1 and soil number 2. That's an interesting observation. We're going to start again with trying to classify the soil, so we come back to our good friend the number 200 sieve, and we think, how are we going to tell if this soil now, which looks even finer than soil number 2, is fine enough to pass through the number 200 sieve. And in fact, it would be very hard to measure that if we just took the dry powder and poured it onto the sieve. The particles become so fine that they have electrostatic charge. They might just cling onto the wire mesh. If we wanted to know the precise percentage of fines, what we would do is mix this powder up with water, and we would wet sieve the material. And if we did that, what we would find is that all of this soil number 3 actually can pass through the number 200 mesh. So all the grains are fine enough. They're less than 75 microns. Okay, I just have to tell you that because we can't do the wet sieving process here as part of the video. But what we can do is look at the comparison with the last soil in terms of the slurry. So I've added some of soil number 3 to water here in this test tube, and we'll redisperse it. And now remember how the other one settled out pretty quickly in terms of the settling front. I'll just hold this here for a little bit. And what we're going to see is this water remains very cloudy for a long time, even up at the top, which suggests there's certainly fines present, but they're not staying completely in suspension. If you look at the bottom, you'll see actually this darker gray material is solids content that has settled out to the bottom. So in fact, this soil number 3 is finer than the number 200 sieve, but maybe not necessarily a lot finer. So how would we go about classifying it? We're into a new category now. If all the soil is passing through the 200 sieve, it's now considered a fine-grained soil. And so we stop considering the particle size, or at least the mesh and the gradation aspect of the soil. We shift the classification questions over to what is the plasticity of the soil. And the plasticity can be measured through Atterberg limits in the laboratory to get precise numbers, But again, we're doing a field visual manual classification, so we want to think more in general terms. And plasticity is sort of like the stickiness of the material. And really it's related to how much do the particles interact with water, and how do they interact with water. And so we're going to do a few simple tests in our hands here just to get a sense for whether we think this is a high plasticity soil or a low plasticity soil. And we're also going to want to get a sense for how easily water can move through the soil. I mentioned earlier that's referred to as the dilatancy of the soil. We've gotten a little glimpse of that here in the sense that these particles have settled out quickly. That suggests the particles are not extremely small, and that we probably have some decent water flow through them, some decent permeability. So I'm going to shake out a certain amount of this soil in my palm, and this is one of the aspects which we'd like to have you all do in person in the lab, if that were possible, but you'll have to watch me do it instead for now. Maybe we'll get a chance at the end of the semester. But what we're going to do is called the shake shine test, and it's an effort to look at the way the soil interacts with water when it's sort of a paste. So I'm spraying some water onto the dry soil on my hand. You can see the water soaks in pretty quickly. I have now kind of a moist pat in the middle. I still have powder around the edges. I'll add a little bit more. What I'm looking for is sort of a thick paste. If I add too much water and the paste gets too thin, which I think I did, we'll add a little bit more powder. Whoop. Got a chunk there. We'll mix it together. That might have been too much, but we'll see. So what I want to do now is, and this looks like it might work pretty well, the shake shine test is sort of an alteration or an altering between applying vibration and static shearing of the soil. So here I have static shearing. I'm pushing it around, I'm failing it, and if you were to describe how it's failing, you might say it's cracking, or it's crumbling, or it's breaking. You can see sharp planes where it's failing. Okay, so it's acting sort of like a brittle solid. But when I apply vibration, by shaking it, by tapping my hand, what do we see happen? I'll have to stop so you can see. We get this bright shiny surface on it. Okay, hopefully you can see that with the lights in the camera there. That bright shiny surface appears when we apply vibration, when we shake it, and then when we stop and we shear it again, that shininess goes away and we go back to having sort of a crumbly material in our hands. Okay, so that's soil that is responding well to this shake shine test. Again, a quick vibration and the static shearing results in these cracks. Okay, so this soil is considered highly dilatant because of the way it is behaving in this shake shine test. And what is it that we're really doing, and what are we seeing? The key is that shininess that we see on the top surface after we shake it, right? You probably know what that shininess is. It's not reflections from the solid particles, it's the water. So there's a film of water that comes up to the top surface and that reflects the light back to you. That water then is moving through the soil as I shake it and coming up to that top surface at the same time that the particles are settling down through the water, right? So the water is able to move freely through this soil. And that's really what high dilatancy is. So that suggests then these particles are not extremely fine. These particles are not holding on to the water molecules around them in the way that a strongly plastic soil would, and in the way that a very fine soil would. Clay particles, of course, are typically at least much smaller than silt particles. And so the shake-shine test behaving like this suggests that it's highly dilatant. The particles are not extremely small, even though they're smaller than the 200 mesh. It's behaving like a non-plastic silt. Okay, it has low plasticity, high dilatancy, and it is mostly silt-sized. But again, remember, when we get to these fine-grained soils, when we say something is a silt, that's not really referring to the particle size in terms of the classification, right? It's a low plasticity silt, or non-plastic silt, being zero plasticity. Okay, so there's one other aspect of low plasticity soils that we can sort of check and confirm our observations here from the shake-shine test, and that is to take slurry like this that's been rolled into a ball and dry it out in the oven until you've driven off all the water. And so what we get left with is a small dry bead of this material. You couldn't do this with sand, right? If you dried out a ball of sand, it would just be a flat pile of sand. But with fine-grained soils, you can usually form a dry clod, so to speak. And the question then is, what is the strength of this? Does it have high dry strength or low dry strength? And so we're going to do a little compression test here with our fingers, and I'm going to hold it over the cup so I don't make a mess. And we want to look at both how it fails and how much force it takes to fail. You're going to have to take my word for how much force it takes, but you'll be able to see the mode in which it fails. So I'm going to get it between my thumb and forefinger and hold it here, and we're going to just squeeze. And well, I can tell you that there's little particles of this soil now, not only in the bottom of the cup and between my fingers, but also all over the table. So we sort of had an explosion of the material. The dry strength was not high. I didn't have to squeeze it very hard in order to have that crumble basically back into the dust. And so low dry strength is also associated with low plasticity, and that gives us good confidence in saying that this is a low plasticity fine-grained soil. Finally, we also want to think about how else we would describe it, right? Color. We can't say much about angularity or individual grains because we can't see them. We can't say much about moisture or density because it's a bulk sample and not intact. So there isn't too much to say there. Moving on to soil number 4, we have a material that looks a lot like soil number 3 visually. It's perhaps a little greener and a little less gray, but it's also a powder. The other interesting thing that I can tell you is that although there's more volume here of soil 4 than soil 3, actually the mass of soil 3 is much higher. So this is kind of a fluffy powder that we're working with here in soil 4. Again, our first question is to decide if it's coarse or fine-grained. It's a little hard for you to judge without being able to handle it, but if I get a little bit on my fingers and just rub it together, you'll see that it's basically a powder that in fact all of it would pass through this fine-grained sieve. So it's not a coarse-grained soil, and we will then proceed with trying to decide whether it's a silt or a clay and high or low plasticity. So we'll go back to, again, not looking at it as a powder, but fine-grained soils in nature exist almost exclusively in the context of moisture. It could be saturated or not saturated, but at least some moisture. So you can see again that powdery nature, right, as I just make a dent in it. It looks like moon dust or something like that. So we're going to add a little water and we're going to compare what happens with what happened with soil 3. And this is interesting. I've sprinkled some water on the top and now it's soaking in. It's taking a little bit of time. At first it was just accumulating on the surface. And so we will try again to run the shake shine test. To do that, of course, we have to bring it to that consistency of a paste, a spreadable paste, you might say. And something else that we should keep in mind about what plasticity means, what plasticity is that a soil with high plasticity is one in which a small change in the water content, the amount of water we add, creates a very small change in the consistency. So we change the water some and not much changes about the consistency. Whereas a low plasticity soil, if you add a little bit of water, it changes a lot. The nature of the paste or the fluid changes a lot. And that's in keeping with sort of the image we have of a plastic soil behaving sort of like a sponge. It'll just keep soaking up more water. And so as I work with this and keep adding more water, trying to get it to a good consistency for the shake shine test, I'm noticing a couple things. One is the consistency is not changing very much. I don't have much soil. I keep adding more water and it gets a little bit softer each time, but not much. So again, that's consistent perhaps with it being a higher plasticity soil. I think I also mentioned that we often think of plasticity as being stickiness, and if you look at my hands, you can get a sense for the fact that this soil is not that easy to work with. I have as much soil on this hand now as I do here almost. But so we'll try to run the shake shine test and we'll see if we can get the water to move through it. There's maybe a little bit, well, no, I don't think so. I think it's just right there. And as I try to shear it, I don't get any of those cracks that I saw with soil number 3. It's not blocky. It's just more like a paste, a thick paste still. So let me try to shake it some more. Yeah. So we're seeing a very different result. We're seeing a very low or non-dilatant soil or response. It's also appearing very sticky. And there's one other characteristic that when we run this test in the lab is also a very good indicator of plasticity, and that is the wash test. And that is after you've gotten your hands dirty like this. There's 2 or 3 sinks in the lab, and it's time to wash our hands and get ready for the next soil. And we line up at the sinks, and it takes about 5 minutes to wash this stuff off. So the stickier it is, the more it clings to your hands, the more you have to scrub to get the soil off your hands. That's also an indicator of higher plasticity. So this soil is consistently looking like a high plasticity soil. I'm going to put this into another separate ball. And before I go clean off my hands, we'll finish up with talking about soil number 4 by looking at soil 4A, which is the loose little sphere on the plate. And as we talked about with soil 3, an indicator of plasticity is the dry strength that you may have when you remove the water after it's been wetted and you remove it in an oven or something. And so we're going to repeat our little experiment. I don't have an extra little cup here to hold it in because I know the answer already, what's going to happen. And that is, no matter how hard I squeeze with my thumb and forefinger, maybe even the palm of my hand on the table, this can't be broken. This is a very high dry strength material, and that's consistent with the high plasticity that we saw from the stickiness and from the fact that it kept absorbing water without changing its consistency very much. So go ahead and classify and describe soil number 4 on your sheet, and I'm going to go wash my hands. So let's look at soil number 5 now, and this one looks a little more interesting. The first 4 soils were a little artificial in the sense that they were sort of pure soils and not an everyday soil you'd find in the backyard. Of course, you might find this one at the beach, or this one, I suppose. But soil number 5 here is from Briones Road, near Briones Park. It's local to here, and it's kind of interesting natural soil to look at. So let's start with that. We're going to come back to our question, the key first question, and that is more or less than half of this soil going to pass through the number 200 sieve? Okay, and of course you might wonder, there's a very big chunk here. As I pour it out, it's quite possible that there's an uneven distribution in my cup, so I probably want to make sure I have a representative sample. But let's just think for a moment. Do we think that more or less than half would go through here? And as I mentioned with soil number 3, we wouldn't probably want to just do it dry, right? Because we'd want to wash or wet sieve the material through to see whether the particles would pass through or not. And if we tried to do this dry, of course, there's these pieces here that would all be retained on the number 200 sieve, and way more than half of the mass would probably be retained if we just did it dry. But there's another subtle effect of wet sieving, and that is the soil would necessarily it would not be possible for the soil to maintain the high sort of dry strength that we just saw. So what happens if you have a high plasticity soil and you try to classify it dry? You might end up with particles, or I should be careful with the terms I use, pieces of the soil that look like particles, looks very angular, but in fact they're not particles at all, right? There's actually millions of particles in this clod, or this dry clump of soil, that are stuck together because as a soil with some plasticity anyway, it has some dry strength. And so you have to get this soil wet in order to even know whether these big particles are really particles, or are they aggregations or clods of many, many small particles. And so we'll add some water, and in fact, oh yeah, look at this. I'm getting very muddy water in my hand, and I'm getting some breakage. And of course, a high plasticity soil is not very permeable typically, so it also takes a little while for this soaking soil, or soil soaking in water, to fully realize when it's going to be in equilibrium. But in fact, what we're getting here now, instead of those large clods, is a paste. Okay, so you want to be careful when you see dry soil and not just visually decide whether particles are coarser or finer than the 200 sieve or even the number 4 sieve, right? Some of those clods were big enough to be considered gravel if they were really their own particle. But in fact, when we get this wet, when we soak it, we would find that probably 80 to 90% of this soil does pass through the number 200 sieve, the fine sieve, okay? So that's well over 50%. So from a classification point of view, we're talking about a fine-grained soil, a silt or a clay, and we need to classify it in terms of its plasticity. So we're back to looking at the shake-shine test, the dry strength. We already had some dry pieces where we could look at the dry strength, and it's pretty significant. I mean, I can break these, but it takes some effort. Okay, so the dry strength is pretty high. That's why those clods have survived that way in handling and storage and handling. So the dry strength is reasonably high. How sticky does it look? Pretty sticky. If I add some water, how quickly does it change its texture? Not very quickly. Okay. And then the last step is the shake-shine test. This is too wet at the moment to really ever behave like a solid. I don't want to add a big chunk though. Let's add some little pieces, grind them up. So that's better. Okay, so I have my thicker paste there in the middle, and we want to check out the shake-shine test. It's shining around the outside on my hand, a little bit of a shine on the inside. So it's behaving less plastic than soil number 4, but more plastic than soil number 3, sort of in between, where it has mild dilatancy, slight dilatancy. That's what we're seeing as I run this here. So as a more realistic soil, this one was non-plastic. This one we saw was very plastic. So this is more in-between material, probably closer to the A line in the Atterberg limits plot. And what do you think about it being a clay versus being a silt? What would tell us something about that? The movement of water through it would tell us something about the whether the liquid limit was high or not. Okay, so we can judge whether we think this is a C, H, or CL perhaps, near that boundary. Okay, and of course in terms of description then, especially if you were describing the dry soil, you would want to make it very clear that it's dried into aggregate clods that are not individual particles. It's whatever color you would like to call that. It's sticky, it's mildly dilatant, and again, because it's a bulk sample, we can't say much about its stiffness or its density or its water content in situ. But we will be able to talk about those things with our next sample, which is soil number 6, the last one. So let's talk about soil number 6, which is in a lot of ways the most interesting of the soils. It's the one soil that we have today that's not a bulk dry sample in the laboratory, but is in fact a chunk of soil that was retrieved from the field, from below ground, using a tube sampler that was pushed down through the soil in a borehole at a certain depth, trying to minimize any disturbance to the soil and keep it in its initial condition. So maintaining the water content and the density without straining the soil, retrieving it so that we could test it in the laboratory and measure properties that relate to its field behavior. So this is now a sample where we can talk about things like the moisture content. How moist is it? What is the density? What is the stiffness? Or consistency, as they say in the standard. So we're going to handle that a little bit differently. We will come back to the sieves and trying to estimate the USCS classification. But we're going to do a little experiment first. So if we were all in room 410 doing the lab together, you would all have a little block of this to work with, and you'd all do this experiment with me in parallel. But this year being what it is, you'll have to watch and just see what happens as I do it. I'll try to go slow and keep it close enough to the camera. So what I'm going to do first is take this oblong piece, and I want to see what sort of behavior it has when it fails. So I'm going to try to fail it in bending. I'm going to take my fingers and do this. I want to see if it will fail in bending. And indeed, well, it really kind of in shear, right? If we look at those surfaces, they look a little rough, but they're kind of planar. They don't look wet at all. I can tell you from the texture that the material is cool. It does feel like it has moisture in it, but it's not shiny. And in fact, the surfaces there look sort of like suede or something like that. It has sort of a roughened texture to it. And it failed sort of brittly, right? So now I'm going to set aside 1/2 of that, and I'm going to do a different sort of a simple test in my fingers. I'm going to hold up sort of a column in my hands, and I'm going to repeat that test again just to get a sense for what compressive strength this has. So I'm just going to squeeze my thumb and my finger together, and what happens? I get another shear failure. Okay, so I was pushing vertically, but my column sheared along a surface. It localized there. That's kind of interesting. And I have two pretty smooth shear surfaces now because I kind of pushed one over the other for quite a ways there. Didn't require a lot of force to fail it that way. So this is certainly not like a dry strength test. This material is moist. Okay, so now what I'm going to do is completely different. I want to remold this soil. So again, the soil structure was intact from the sampler and as we did these little tests, but now I want to completely remold the soil. I want to mix it up completely so that all the particles are in a different configuration than they were in the natural condition. And something really interesting happens when I do that. Okay, look at my fingers. I can tell you that the material is getting sticky the more I mix it. And in fact, it sure seems like it's getting wetter and wetter. Now, it's not raining here in the lab. We're not adding water in any way, so this is a little bit of a mystery. We need to figure out what's going on there. Once it's completely reformed, and if I can get most of it off my fingers again, I want to reform that into a bit of a sample like I had before, tall and thin, prismatic sample. Okay, and now I'm going to retest it, and I'm going to see that a couple of things are different. Now it takes even less force, even less squeezing for me to fail it. It's weaker than it was a minute and a half ago, and the failure mode is completely different, right? I didn't get a shear plane at all. I got basically just kind of a squashing of my little sample. So we've changed the nature of the material from being a brittle material to being more of a plastic material. It's also, as I said, seems much wetter and much stickier. So what happened? What's going on with this soil, and what is it? If we were to rigorously test it with wet sieving to see how much of it went through the number 200 sieve, we would find that virtually all of it went through the number 200 sieve. So it's a fine-grained soil. It occasionally has a little bit of sand in it, but it's not relevant to its behavior really. So that leaves us with the classification we've been doing for fine-grained soils. Is it high or low plasticity? And interestingly, it sort of seemed to change. Initially, when I was shearing it, it was brittle, it was dry, it seemed like it wasn't very sticky. But now, through remolding the material, we've turned it into something which is much more like soil number 4 and 5. And in fact, if we were to take this, it's actually not at a bad water content for that. If we were to try and do the shake shine test, it would be hopeless. We wouldn't see any shininess. It's not going to break brittly in this condition. So it's not dilatant, and it is quite sticky. So in terms of its classification, now remember its classification is independent of its initial condition. So its classification is going to be based on these observations we have, and the fact that its dry strength is actually high, this material. It is actually a high plasticity clay. But that doesn't explain what we saw at the beginning. And so what's important to know, this material is called San Francisco Bay mud. It's sort of a famous soil in this area. It is deposited in such a way that it's very structured. And in other soil classes you'll hear more about the factors that go into that, or maybe in engineering geology, but the way the material is deposited and then the history beyond that, the way it's leached, leaves it with a very loose structure and a very high water content. You can see here the water content is quite high, as if I had added water. But in fact, in its initial condition, that water is essentially hiding in large voids. The clay particles that are in this material form sort of a card house structure. We say that the particles are flocculated, meaning they're sort of edge to face, and that leaves large voids between the particles in which water can exist in its natural condition and sort of hide. And so that initial strength that was a little higher was the strength of that card house structure. But once we broke that structure down and remolded it, we basically effectively did raise the water content and lowered the strength consequently. And these kind of materials that initially exhibit a higher strength and then when they're remolded see a drop in strength are called sensitive soils. And in this case, this is a sensitive clay. Bay mud, San Francisco Bay mud, is a moderately sensitive clay. because of the behavior that we're seeing here. In terms of its description then, we would want to mention these things. Initially it seemed drier, it was soft, or yeah, I would say soft initially and very soft when it was remolded. It has significant sensitivity. It is what color? Sort of blue-gray. Sometimes it's a little green-gray. I'll leave you to complete the description then of soil number 6, and this is the completion of the first lab.